Kinematics in 2 dimensions summary. Let's start with vectors. We're going to talk about unit vectors first. Unit vectors describe directions in space. They don't represent any physical quantity per se, like velocity or acceleration or position, but they will help you describe it. They have a magnitude of 1. It's a vector with a magnitude of 1. And we're going to have I hat. Yep, that's what you call that little caret on top. I hat indicates the x direction. So you can see here's your x-axis, here's your unit vector I, and you can see the length is real small here. That's a length of 1. J will indicate the y direction. K hat is the z direction. Any given vector can be presented in terms of unit vectors. So over here, let's say you just want to talk about a vector in the x direction, a sub x, that would be ax, which is the magnitude of a sub x, times I hat. And if we put it all together, a vector A, which is in 3 dimensions, would be a sub x I hat plus a sub y j hat plus a sub z k hat. We will have a position vector called r, and if you look at the picture over here, r starts at the origin and goes out to this corner here of this rectangle. And we're going to start the object at the origin and we'll move it to point A. And we're going to do it in a couple steps here, 3 steps. And we can really do it in any order, but let's start going out in the z direction here, then in the x direction here, and then up in the y direction. And I'll erase all those guys and show you where we wind up. We'll wind up right here, and then connect that to the origin. And we're going to call that vector r, and it will be ax I hat plus ay j hat and az k hat. And each individual a sub n, is the magnitude of the position vector in those 3 directions. So by adding these 3 vectors together, we will wind up with the total position vector r. And we'll put that up here. From the position vector r down here, we can then build instantaneous motion for velocity and acceleration by going up the ladder here. V will be the first derivative of the position vector, which is dx dt I hat plus dy dt j hat plus dz dt k hat. Then we'll go up one more level to find the acceleration similarly. And what do you notice there? There's a key. Motion in each of the 3 dimensions is independent of the other dimensions and is solved for separately. The previous slide took you from position, the r vector, up to velocity, then acceleration through differentiation. Now we're going to go the other way. We're going to use integration. We're going to start with the acceleration vector, and then we're going to move down this way by subsequent integrations. We're going to assume that x0 equals y0 equals z0 equals 0, and the object starts with the 0 velocity in all 3 directions. In that case, we'll represent the velocity vector as integration with respect to time of acceleration in the I direction, the j direction, and the k direction, and they are all independent of each other. We do one more integral to get down to position. Right? We'll be integrating the velocity vector in x, y, and z directions. Now, what if these boundary conditions up here don't hold? Well, then you'll have to do a definite integral with limits of integration. For example, if you start at position x equals 3 and go to x equals 6, you would integrate, let's see, what are we going to do here? Let's say you have the velocity, and I gave you those initial positions. You'd be integrating, and I'll just erase this so we can see it a little better, down here. Okay, so if I started the velocity at 1 meter per second and went to 5 meters per second, you would have a 1 here and a 5 over here. And you would have that for each one of them because the time would be the same in each direction. So that would be a definite integral where you're given the time limits. If you're not, then you do an indefinite integral and you solve for the integration constant. On this slide is pretty much everything you need to know about the motion of a projectile, where you start at one level here and then finish at the same level. It shows you the velocity vectors in the x and y component. Notice we're doing 2 dimensions now, not the 3 that we showed. And in the x direction, there's no acceleration, so that term drops out of the second kinematics equation. For the y direction, we do have an acceleration, and that's negative g, so you put that in for a. And for the velocity, your initial velocity is your final velocity. It's your velocity throughout the entire problem in the x direction. In the y direction, it's this, where you have the acceleration due to gravity acting on you. No acceleration in the x direction, and of course the y direction is minus g. The first thing you do on projectile motion problems, if it's shot off at an angle there with respect to the horizontal, break v into its x and y components and we'll solve them independently and then combine them at the end. So here's the trig that tells you what they are, and then at the end of your problem, when you find vx and vy, you put them together with Pythagoras to find the final velocity, and the angle is found here with the inverse tan. We won't derive these equations here for the maximum height and the maximum displacement and time in the air, but you can refer back to the Kinematics in 2D presentation notebook. And once again, this is for assuming the projectile lands at the same height as its initial height. We will have a maximum height given by this expression. This is our time in the air before it hits the ground. And you can see that if you fired at one level here, and let's say instead of landing here, you had a little cliff here so it landed below, this is not true anymore, right? Because the time just takes you to this point. So you have to use the second kinematics equation to figure out how long it takes to get there. And then of course that would also change your maximum displacement. But these equations will work when you shoot it off at one height and land at the same height. Another type of two-dimensional motion is uniform circular motion. That occurs when an object moves in a circle, okay, that comes from the circular point, but the uniform means it has a constant speed. The speed stays the same. Of course, the velocity keeps changing because the direction keeps changing. Another key point is the acceleration is perpendicular to the velocity. And of course, the velocity and displacement vectors, so delta x or whatever you'd like to call it, are tangent to the circle. This perpendicular acceleration is called centripetal, which means center-seeking acceleration. The acceleration is caused by a centripetal force. For example, if let's say here's some kind of ball and you're in here and you're spinning it around over your head and this is a string, the string's tension force is providing a centripetal force which keeps the object moving in a circle. Now when that force is perpendicular to an object's displacement, what do you know about the work done? Well, there's no work done, right? If the force is perpendicular to displacement, F dot D will equal 0, so no work. With 0 work, the work energy equation states that the kinetic energy final equals the kinetic energy initial. We'll assume that the potential energy is staying the same. And the speed will remain constant. Therefore, we have Newton's second law, which is ma centripetal equals mv squared over r, where v is your tangential velocity. A key part of making motion measurements is to have something to measure the motion against, and that will be a reference frame. There is no preferred reference frame, and frequently there is need to translate measurements made in one frame to another frame. In other words, the same motion but measured in different places. There's a specific kind of reference frame, an inertial reference frame. That has a constant velocity relative to another frame. It is not accelerating. Measurements from one inertial frame to another may be translated by Galilean transformations. Here we have two frames. We have the XY frame, marked A, and here it is, there's Y, and here's X, just like that. Okay, so hopefully you can see that. And we have an object here at point P, and its position vector measured in frame A is RP, P is the point, relative to A. So let's erase that now, so hopefully you've seen it. We have another reference frame B, and that is denoted by Y prime and X prime, and that is over here here, it measures point P with a different measurement, right? It goes from its origin to here, so it's R of P relative to B. So let's take that, and now we have one more thing to add to this story. Reference frame B is set in motion with a constant velocity VB with respect to A, and in a time t, it covers this distance here, VBA times t. So a couple things you notice about that is, one, they will each have different measurements for where point P is, and the other one, the critical part, is VBA is constant, so we can use the Galilean transformation. There is also no transformation in direction perpendicular to the motion. If you look in both frames and you look at the y or the y prime coordinate, it's the same for both of them. So there's a notion here that you have to be moving for your measurements to change. So what we have, the position as reference frame B is moving of point P relative to A equals the measurement from point P to the reference frame B plus this velocity times time. And then we have the velocity one, where the velocity of PA, let's say point P is moving itself, that will equal the velocity of point P relative to the B reference frame, that's the moving frame, plus the velocity of the velocity of the reference frame B compared to reference frame A. So let me take those away so you can look at the letters. And once again, note that in the y direction, they have the same measurements for point P, no matter how it moves. What if point P is accelerating? Okay, so what if P is maybe a race car and it's speeding up, it's increasing its speed? So we take the derivative of the Galilean transformation of velocity. So here's the velocity one. VPA is equal to VPB plus VBA. And a nice thing to notice is look at the subscripts here. See how the two B's are there? You can visualize those canceling out, and then you'll get velocity of PA, which is right over there. So we now take the derivative of all of that, okay, because we want to talk about acceleration, and we get these two. However, what's the derivative of the velocity of BA with respect to time? Well, that's 0, because VBA is constant for an inertial reference frame. So what we find is the acceleration as measured in both reference frame of point P as it moves around is exactly the same. So here it is again in italics. The acceleration of an object measured in two reference frames moving with a constant velocity relative to each other is the same.